Hello everyone. So you are watching the very first bonus video in our research skills analysis of variance course. So this is a bonus video in which I will tell you how I actually carry out a multiple hierarchical linear regression analysis. It's called multiple regression, as you know, because there will be more than one predictor. It is hierarchical because we are going to use more than one model. I'm going to use the first model and then make that very first model a bit more complicated by adding another predictor in this case. Comparing those two models and adding predictors in a hierarchical way, that's why it's called hierarchical. Right, so it's actually my birthday today. See? And actually, the weird thing about Dutch birthdays is that Dutch people typically give away things on their birthday. So usually this is cake or sometimes cheese. But since we can't do that this year because we can't really meet in real life, I'm going to offer you this bonus video. So this is my present for you. I hope you find it useful. So before we start, let me show you first two slides. So I have to share my screen again. There we go. And the first slide, just to remind you of those checklists yet, right? So by now, I think you must be familiar with those checklists, so you can find them on Canvas. And here you see a part of the checklist for multiple regression analysis. And when you're carrying out an analysis, it would be very good if you just go through this checklist step by step, just ticking boxes whenever you've finished one part of the checklist. And for multiple regression, right, there are many, many assumptions to check. As you can see here, there are 7 in total. So I'll show you how to do this actually. So the checklist tells you what to do, but of course then you don't know yet how to do things. So I'll show you how I do things, and then you can take that as an example just to be sure that you're doing things in the right way. So just looking for ways to make sure that you carry out things in the right way, such that you know how to do things after this course. One way of more or less being sure of this is those checklists, but I think this bonus video is also going to help. So typically students are, of course, doing those practice assignments in university in a computer room, and then I walk around, and if they get stuck, then they ask me what to do, or they can double check with me whether what they are doing is actually correct. That's something we can't do now, so therefore I think this video will also help in addition to those checklists. So I hope the combination of those two things will really help you to be sure that you're doing things in the right way. Another thing that I wanted to share with you, based on also some of the questions that were asked via email to me, I think maybe the even most important insight that I could teach you is that basically statistics is not a black and white discipline. So what do I mean with this? I mean that different researchers have different preferences. So today I'll show you how I carry out a multiple regression analysis, while different people may do this in a different way. For instance, with regards to those assumptions, right? So we have those 7 assumptions for multiple regression. Some of those assumptions I will check in a certain way, but other people might do this differently. So perhaps your stats teacher during the pre-masters or during your bachelor's might have been doing things in a different way. That's because statistics is not a black and white discipline like communication and information sciences. So there also people have different opinions, people have different preferences, people do things in different ways. And there's a lot of discussion about this, which is good because that's how things work in science. We're constantly discussing how to best do things. That also holds for statistics, also for instance for testing assumptions. I'll show you how I do things, but different people may do things in a different way. If you have a different preference, that's perfectly fine, as long as you sort of can argue, come up with some arguments why what you're doing is correct. It also, for instance, holds for effect size measures, as we have seen. So some people for effect sizes, they report eta square. Other people report partial eta square. Yet in Andy Field's book, you might encounter this omega value as a measure of effect size. He prefers that. Me, myself, I typically prefer partial eta square. It's just a different preference. Different people have different preferences. And so like this, there are many different things that you can do. Also, sometimes people report R square to show how well their model fits their data. Other people prefer adjusted R square. So there's not just one right way of doing things. So different people prefer different things. And I think that's maybe even the most important insight that this also holds for statistics. All right, then let's now move towards SPSS. And to do so, I have to stop sharing this screen. Hello. And then I have to share another screen. Right, and here we are in SPSS, and I'm going to use the data set for the practice assignment for week 4. Just as an example, so I'm not going to literally do what you have to do for the practice assignment for week 4, but I'm just using the same data set because it's a huge data set and I can nicely illustrate many different things on the basis of this data set. So typically the first thing I do when I receive a data set like this is just to look at it and see what's in there, basically. I think that's the best thing to do if you see a data set like this for the first time. So in this case, here we are in the variable view, and of course you also have this data view, right? That's here. There's all sorts of data in there. It's a very big data set, that's why it takes some time for SPSS to load it. But let's start with this variable view. So typically the most important things are on top. So here you, for instance, see that this first line here probably refers to conditions. Here, let's make those labels a bit more visible. So here, in this experiment, apparently there were experimental conditions and then the values were 0 or 1. So it looks like in this experiment, there were two different experimental conditions. That's good to know. There's participant numbers. Each participant probably has their own number. There's a dyad number, which probably means that participants took part in dyad, so in groups of 2. While their age has been elicited. Also their gender, which is probably male or female in this case. Yeah. Only 2 genders here with old school. And then it looks like as if there are a lot of different questions or statements that have been asked in a survey. So my conversation partner is pleasant to be with. Here, apparently, people could have agreed with this or disagreed with this on a 5-point scale. So there's also the things that you can simply learn just by looking at those, this information that's in this data file. All right, so those things are good to know. Maybe we should just start by carrying out the analysis. So as you know, for each analysis, there are several things you have to do. The most important thing is checking assumptions, unfortunately. For regression, for multiple regression, there are 7 different assumptions to check. And most of them you can actually check while you're asking SPSS to carry out the analysis. So for a multiple regression analysis, what you do is you go to, surprisingly, regression. And then you select linear, which is the basic default option. There we go. And here, as you probably already know by now, you can enter your dependent variable, right? So let's do that. So in this example, like in the practice assignment for week 4, we're going to take social attraction as our dependent variable. And then here in this block, you can start entering your predictors, which are also sometimes called independent variables or factors. Let's call them predictors. And now let's, in the first block, so block 101, let's enter the predictor uncertainty. So in this data set in general, in this experiment, what was going on was that people had an initial interaction with each other. So they met for the first time and then they had a short conversation together. And those researchers, they measured afterwards their social attraction on the basis of a survey with different questions. And they wanted to see what predicts this social attraction. Well, on the basis of the literature, we know quite well that people's uncertainty is a very strong predictor. We already know this, but it's good to still check this. So therefore, because we already know that this predictor is probably going to have a very large effect, we enter it here in the first block. Then we go to the next block. And what's very confusing about my version of SPSS, which is the latest version, maybe you have the same one, So now we're in the second block, but it still says block 1 of 1. So this is just a bug in this version of SPSS. So this is actually, we are actually here now in the second block. You can see this by going back. So now you can't go back anymore, right? So previous is being what you call it, is no longer possible to call to click on previous. This must be the first block. So this is our one predictor, right? If you go to the next block, this must be the second block, but it just says block 1 of 1. A bug in SPSS. Let's call searchbot and ask back our 10 euros. Now in the second block, let's enter, for instance, people's openness. So this, how open people are, does that also predict the social attraction in their initial conversation, in their initial interaction. So this is in the second block. Based on the literature, we don't really know that much about openness, so this is more exploratory. That's why we put this variable in the second block, this predictor we put in the second block. So basically in this example, we just have a relatively simple setup. So in the first block, we have one predictor, which we know that it has quite a big effect. We already know this on the basis of literature. Then we're going to look into a second model, into a second block to see whether on top of that, openness also adds something. Is there any variance left that this additional predictor can explain on top of the uncertainty predictor? So what you could do here is enter uncertainty again, but you actually don't have to. So actually SPSS already in your second model, in your second block, always includes what's in your previous block. So your second model will consist of openness and also the predictor from the first block. See whether this joint model is better than the simple model with just uncertainty. Right, so this is just for specifying your models. But of course, we're also going to look at assumptions. How do you check those 7 assumptions, the 7 types of assumptions that you find in your checklist for multiple regression? Well, nicely, there are those buttons that we have here. And let's just start with the first one, statistics. And there we can actually simply tick several boxes. So here, for instance, what you see here is this Durbin-Watson term. And this actually relates to one of your assumptions, right? Because this is also what you see on your checklist. So let's just tick this box. And in this way, we already tick the first box for the first assumption. Here's another nice box, case-wise diagnostics. This box actually refers to the outliers that there might be in your data set. So this is already related to your second assumption, related to those outliers. You have to check the assumption that there are not too many outliers in your data set. Well, actually here, by default, SPSS says outliers outside 3 standard deviations from your mean. Actually, in general, there are not too often that many outliers outside 3 standard deviations from your mean. So it's probably a wise thing to do to change this number into 2. And then you get a bit more information later about your outliers. All right, so that's the second assumption already related to outliers. Then there's Durbin-Watson. And also here you see this term here, collinearity diagnostics. That's actually something you have to tick for your multi-collinearity assumption. So that's already also in the statistics book, already the third assumption that you can check simply by ticking this box here. All right, then it's also probably nice to have the R-squared change when comparing different models. It's also nice to have the descriptives, of course, just the mean value per condition and the standard deviation per condition. And it's also here important to select those correlations because you want to know later whether your different independent variables, whether your different predictors actually correlate. So also tick this box. And it's also nice to have confidence intervals. So I would also tick that one. So in the statistics dialog window, this is what I typically check, what I typically tick in terms of boxes. And already it relates to 3 different assumptions out of 7, right? So that's already pretty nice. All right, so that was the first button. Let's go immediately towards the second one, this plots button. And there again, we can test several assumptions. So we have 3 done now. One other thing you have to check, one assumption is related to the normality of your residuals. How I typically check this assumption is by asking for a histogram of the residuals and by asking for this normal probability plot. So those 2 things together I use to check whether the residuals are normally distributed. So remember that in multiple regression, you're not checking whether your data are actually normally distributed, but you're checking whether your residuals, so your errors, are actually normally distributed. If you no longer know what I'm talking about in this case, have a look again at the video lecture for the very first week where I also explained this. So if you want to check whether your residuals are normally distributed, you tick those two things. And here you can actually also ask for some scatter plots of your residuals, which will also be helpful. So therefore, you need to enter the z-score for your residuals here and the predicted values here. Can also be the other way around. Doesn't really matter which way around you do this, as long as you pick those two. And then I typically also ask for partial plots. So this will give you a scatter plot of those things, the z-scores for the predicted values and the residuals together, plotted as a scatter plot. And this will also actually tell you something about some more assumptions related to the homoscedasticity of your data and also the linearity of your data. So those are two more assumptions. And then there is the histogram and the normal probability plot for actually the normality of your data. So another assumption. So based on this box, again, we have three different assumptions checked. So linearity and heteroscedasticity or homoscedasticity. Those are two, and the normality. So if we continue already, we have actually 6 out of 7 assumptions covered already. So there's one more to go. And that one you can get under the save button. And there actually we have to tick those 3 boxes. So remember that you're also going to look at cases that are influential, influential cases. So this is a bit different from outliers, but quite related. And for influential cases, your checklist tells you need to look at those 3 things. So you can simply tick them here. Let's forget about the rest now. Let's just tick those 3 boxes, and then we've also covered our 7th assumption, actually. All right, continue. So now we have told SPSS to give us all sorts of information about those 2 models that we have, those 2 blocks, and also about those 7 assumptions that we have. So now we can actually tell SPSS, okay, now start running this analysis and also give us all this output about those different assumptions that there are. So we press OK. And now what I'm seeing is the output, but I learned this morning that you're not seeing the output now. How did I learn this? Because I was recording this entire video and then watched it back myself. And then I found out that I was talking about the output, and pointing at all sorts of different things, while you actually did not see this. So that's why I'm recording this video for a second time. All right, one more thing before we start looking at the output is that for those influential cases, you actually have to do a second thing. So you have to tick those boxes, those 3 boxes, right? But you also have to do one additional thing to actually get the important information that you need for those influential cases into your output that SPSS gives you. What you have to do for that is you go to Analyze Reports, then select Case Summaries. There you go. And now you will see that because you tick those 3 boxes, actually SPSS has given you 3 more variables in your data set. Those 3. I already did this before this morning. That's why I have it twice here. But if you just do this once, you have this you only have those 3 different things once. You select them, put them in this variables box, and then actually also tick this option here, show case numbers. And one other thing that is important here is that SPSS is actually quite lazy. SPSS by default just wants to give you output for 100 different cases in your data set. Actually, in this data set, we have 200. So check how many lines there are in your data set and change the number here such that all of your different lines, all your different cases are included, all your different participants are included. So in our case, this is 200, so I'll change this to 200. Then I simply press OK. And now SPSS is also giving me this output that you probably still don't see. All right, so what I should do now is stop sharing this screen, and then we're going to move towards interpreting the output. So I'll stop sharing. Now I should share with you the output that we have. Let's see where it is. There it is. Right, and now I very much hope that you see this output. I will only find out later when watching this back. Technology in 2020. All right, so let's interpret this output. So what you first get is those descriptive statistics that we asked for, right? And here, this is very important information because in any study, in any report, you should share actually the means of your different conditions and also the standard deviation or the standard error. And you simply get them here. So this is simply something that you report in your report of your analysis that you always report. We also get this nice correlations table. And you will see in your checklists, before the checklist starts talking about assumptions, it talks about correlations. And for multiple regression, it's important that your different predictors don't correlate too highly with each other, because if they correlate very highly, and I'm now only talking about the predictors, I'm not talking about the dependent variable. If your predictors correlate very highly, this means that they might be measuring the same thing. So therefore, it might be wiser to merge them into one predictor. Well, to make sure that this is not the case, you can check in this table that you're actually that those different predictors are actually not correlated too highly. So in our example, we have two predictors, right? Uncertainty and openness. And you can see here that uncertainty correlates with openness for a value of minus 0.092. That's not super high, so that's good. And of course, it also works the other way around, right? So openness also not too highly correlates with uncertainty. It's the same correlation, minus 0.092. Now, you might think, what is then a good value? What is not? That's something you can see in the significance part of this box. So here you actually see that those two variables, openness and uncertainty, don't significantly correlate. So this value is not lower than 0.05, which means they don't significantly correlate, which is good, right? So they don't correlate. What you also see here is that there's a correlation between the dependent variable and the predictors. This can be quite high, right? But that's good. That's perfectly fine. That's actually what you're actually looking into. Is there any correlation between the predictors and the dependent variable? That's what you basically test in your multiple regression analysis. All right, so here's a small box. You can just ignore it. What you definitely can't ignore is this model summary, right? So I hope by now you more or less know how to interpret this. So here we see our two models, right? We had two models, we had two blocks. In the very first model, there was just one predictor, right? Uncertainty. And in the second model, there was an additional predictor on top of uncertainty. So uncertainty automatically, by default, has been entered also into the second model. But we manually added this openness predictor as well. So model 1 has one predictor, model 2 has two predictors, and our dependent variable was this thing here, social attraction. And what you can see here in this model summary already is that your very first model that just had this one predictor is a significant improvement over what they call the baseline model or a random model. So actually this model with one predictor does significantly better than chance or randomness. What you also see is that the second model is doing significantly better than your first model. So those two predictors together, they lead to a significantly better model of the data compared to your first model that just had uncertainty in there. So that's basically what those significance values mean here. Right, so here you see also how well the model fits the data. And you see that the R-square for the second model is indeed quite a bit higher than the R-square value for the first model. What you also see in this table is this nice Durbin-Watson value, right? And this Durbin-Watson test is testing the assumption of the independence of errors. So your residuals, your errors in your model should be more or less independent. That's what this assumption is checking. And if this value is somewhere between 1 and 3, then you're fine. So here it's very nicely right in between the values 1 and 3 because it's 2, and that's perfectly fine. So here this first assumption, this assumption of independence of errors, is actually being met here. So that's good news. So the first of our 7 assumptions can be has been met. So you can tick the box in your checklist. Very nice. All right, and now let's just move on. This is a ANOVA box that you can just ignore. I always ignore it in multiple regression. Then one nice thing we get is this coefficients table. And that's also quite interesting for two reasons. The first reason is we've seen that our second model is actually significantly better than our first model, right? But in principle, this does not necessarily have to mean that all the predictors in the second model are actually significantly contributing to this. So overall, the second model has been significantly better than the first model, but it can be that you have a model of, for instance, 5 or 6 predictors. It can still be doing significantly better than your previous model, but it can still be the case that one of your predictors then does not individually significantly contribute to the model. Well, this is something the first thing you find in this coefficients box. So in our case, what we see is that, first of all, we're going to look at the model 2, because model 2 was the significant better model compared to model 1. What we find for model 2 is actually that both predictors in there are significant. So both have a significant contribution to explaining the variance in our data. So therefore you report individually, for instance, that uncertainty is a significant predictor of social attraction. And then you report those different values. And also openness is a significant predictor of social attraction. It's also significant, and again, you report those values. That's the first interesting thing about this table. The second interesting thing is those collinearity statistics that we asked for, right? So this is related to your assumption of multicollinearity. You get two columns here, and both can be used to test whether there has been any multicollinearity in your data. What's important here is that this VIF value for all your predictors is actually lower than 10. Well, that's the case, so that's good. And also the average value of those different values here should not be substantially higher than 1. So here, if you take the average, it's just a little bit above 1, so that's good. It's not substantially higher than 1. The second way of checking multicollinearity is by looking at this tolerance column. And there the values actually need to be higher than 0.2. And that's actually also the case here, right? So both those columns tell you that you're actually meeting your multicollinearity assumption. So that's actually the second assumption that we meet. So again, you can tick your box in your checklist. Multicollinearity assumption has been checked and has been met. Okay, let's move on then. This small table excluded variables you can just ignore. Here we get some more collinearity diagnostics, but we already just checked them, so we can ignore them again. Here is another important table, so those case-wise diagnostics. So this actually relates to your outliers. So it's important that there aren't too many outliers in your data, because if there are a lot of outliers in your data, then perhaps those outliers are actually driving your effect. So you wouldn't have a genuine effect, it would just be caused by a couple of outliers that are very much influencing your data in a way that you don't want to. So here what we see is 2, 4, 6, 8, 10 different outliers. So you might think, oh, this is not so good, right? 10 different outliers in my data set, what's going on? Well, actually remember that we have 200 cases, 200 participants in our data set. And if there are 10 outliers on a total of 200 different data points, then that's actually 5%. And it's perfectly fine to have 5% of outliers. That's actually what you would even expect when you would have a normal distribution of your residuals. So having 10 outliers out of 200, when you put this value to 2 standard deviations, remember, that's perfectly fine. You see here that there's only one value that's higher than 3. So if we would have left this value to 3, it would have been only 1. That's often it's more informative to put it to 2, so you get a bit more information. And here, since there are only 10 out of 200, that's 5%. 5% is perfectly fine. So here, this assumption, checking your outliers, has also been met. So that's actually the third assumption that has been met. That's nice. This box you can ignore. Yeah, so then let's move to the next assumption, normality of your residuals. As I told you, I typically check this by looking at this histogram. And here, as you can tell from this black line, those residuals here are very nicely distributed. So this very much looks like a normal distribution. So that's very much an indication that your residuals are actually normally distributed. One other indication for that is this so-called PP plot. And there it should be the case that those data points here should be more or less in line with this diagonal line. And that's also more or less the case here. So both those types of information, this histogram and also this plot here, sort of indicate that the residuals are normally distributed, which is good. So that also checks our normality assumption. Some people, actually some other researchers, check this in different ways. As I said, different researchers do different things. Some researchers check this by using this Kolmogorov-Smirnov test. That's also something you can do, but make sure for multiple regression that you then check this for the residuals and not for the data themselves. I just prefer to just look at those two graphs. It's just easier and also gives you the information you want. So between brackets, one thing I found out that actually also this guy, Kolmogorov or Kogomorov, I always forget which way the syllables in his name are ordered. He's actually also having his birthday on the 25th of April. Isn't that nice? I thought it was very funny when I found out. I think he's no longer alive, so there's no way we can sort of celebrate that together, if that were allowed. One more thing one more thing I didn't forget yet, but that I should tell you now, is that now we're looking at this Scatterplot, right, that we asked for by plotting the standardized residuals compared to the same plot as the standardized predicted values. And this very nice plot actually allows you to test for two assumptions at the same time. So we've had 4 now, I think. So after having interpreted this plot, we have actually checked 6 out of our 7 assumptions. So here, what this plot tells you is actually whether there's any heteroscedasticity in your data. And if there is, if your assumption is not being met, then actually you will find that your data points here have the shape of a funnel. If you don't know what a funnel is, then go to Google Images, type in funnel, and you'll find it very quickly. So in this case, this very much looks like a random array, a random cloud of dots. And that's actually what it should look like. If it looks a bit like this, if it's just random cloud of dots, then you're good for your assumption of heteroscedasticity. And at the same time, you're also good for your assumption of linearity. So if there's no funnel, if this is just a random cloud of dots, then you're also good for your linearity. So in this case, both those assumptions are now also met. So actually 6 out of our 7 assumptions are now met already. You can also ask for those partial regression plots in which your predictor is plotted versus your dependent variable. And then also what I typically do in those are actually also scatter plots. They're just called partial regression plots here. But I typically use those plots for as an additional way to see whether there are any outliers in the data. So here it doesn't really look that there are any very clear outliers, maybe this one, but actually not so much. If all your data points are somewhere here in the corner, for instance, and then there would still be one data point here, then that would be a very clear outlier, right? So then visually you would be a bit more sure whether there would be any outliers in your data. Same for the other predictor here. Again, there's not really one clear or several clear outliers somewhere that are very far apart from the rest. So that's a sort of double checking whether there are any outliers. All right, so those were 6 out of our 7 assumptions in the typical multiple regression output. Remember that we also asked for those key summaries for the different potential influential values. And they're actually those influential cases, I should say. There, remember, we asked for all 200 of our participants. We asked for those different values. The Mahalanobis distance, sounds like a very Hawaiian name to me. Cook's distance, that sounds like very New Zealandish. And centered leverage value. So that's what we nicely got here from SPSS. And we got this for all our 200 cases, right? So they're all 200 in here. Well, the first thing I always do here is check Cook's distance, because that's by far easiest to check, because always, in all cases, Cook's distance needs to be, for each case, needs to have a value that's lower than 1. And actually, if you scroll through this output, you will see that for Cook's distance, all those values in this middle column of the tree, all those values are actually lower than 1. So that's actually a very nice indication that there are no strong influential cases in our data, which is good because that's our 7th assumption, right? Right, the final one. Actually, the other two things here, so this distance, the m distance, let's call it the m distance, and the centered leverage value, the value that those values need to have is actually different for each data set and for each analysis that you do. So this depends on the number of predictors that you have and on the size of your data set. So actually in the correct answers for the assignment for week 4, you can actually read how you should calculate for yourself what the typical cutoff value should be here for those two. It will take too much time to explain it here. So just look at this and try to play around with that a little bit yourself. But it's also a good idea, next to checking this Cook's distance, which is relatively easy, to check those two things as well. All right, and so those are our 7 assumptions and our multiple regression output. So now we've actually carried out a multiple regression analysis. We've looked at all the assumptions were met. I hope you now sort of get a feeling of how you should do this yourself. And then actually you can also start reporting the analysis, obviously. All right, so that's all nice and good. Maybe one thing I can still show you, now I'm talking to you anyway, is something that will become relevant for the practice assignment for week 4, but which is something that we didn't discuss yet in this course. So to do so, we have to go back actually to the data set itself again. So let's move to the data set. There we are again. So I'm going to share my data set again with you. All right, great. Now you should see this data set again. Let's save it. So for this data set, one important thing here is that in all the analysis actually that we're carrying out in this course, there's always just one dependent variable, right? There can always just be one. But actually, if you look at this data set, you will see that for our dependent variable here, this social attraction variable, there are actually 8 different statements or 8 different items, right? So if you would just have this in your data set, it wouldn't be very nice to just enter 1 as your dependent variable. Ideally, you would want to have the average of those 8, right? And have that as one dependent variable that you could enter in your model in the way I just showed you. Well, if you have a data set like this, what you should do then first, before you run the analysis, is actually compute this new variable that's actually the average of those 8 things. And this is something you do by not going to analyze for a change, but going to transform and go to compute variable. And here in this dialog window, you can actually compute a new variable on the basis of those different items that you have. So what I did before, prior to carrying out the analysis, I made a new variable that I called social attraction that did not exist yet. And then I just took the average of the different items. So the average of social attraction 1 plus social attraction 2 plus social attraction 3, all the way up to social attraction 8, right? So there would be all the 8 with pluses in between. And then obviously one thing you should do is divide this by 8 if you have 8 different items, because then you get the average, right? So what SPSS then does for you is that it creates the average in a new variable for your 8 different items. And you can use this very one variable as a dependent variable, for instance, in your analysis. The same actually holds for your independent variables, so for your predictors. So here in your data set, for instance, for openness, we had 6 different items. But of course, it would be nice if you can enter them into your analysis as one predictor, openness. So therefore, also for openness, what I did, for instance, I again went to transform compute variable. I created a new variable called open. Then actually I combined those 8 different, sorry, in this case, 6 different items all the way to openness 6. So if you're doing this yourself, you need to enter all 6, right? So don't be sloppy in the way I'm doing this now. Divide by 6 in this case, and then you'll get your new openness variable in your data set that you can then use as a predictor. One more important thing that I should tell you here is that in this case, some of those items needed to be recoded. So ideally, you want all your items here to go into the same direction. And that's not the case if some of your statements are positively framed and others are negatively framed. Right, so if you go down, you will see, for instance, in this data set that you will also need for the practice assignment for week 4, you will see that already some of those variables, some of those items actually have been recoded. So they end in an R. So social attraction 3 R is actually the same as social attraction 3, but in this case it's recoded such that a positive, so for instance that a score of 1 has become a score of 5, such that all of those things can be nicely added. If you're recomputing your variables, make sure to include the recoded versions of your items here, because then the average is actually meaningful. All right, that's something I still wanted to tell you about computing variables and computing new variables, so you can nicely have one dependent variable and predictors that consist of the average of your different items in this data set. And that's actually more or less what I had to tell you in this bonus video. So most importantly, multiple regression analysis that was hierarchical because we had different models. And there was multiple regression because we had multiple predictors, more than one. And just a brief part about computing your variables because you need it for the assignment in the practice assignment in week 4. All right, so that's more or less what I wanted to say. As always, if anything's unclear, please just send me an email or join the Q&A session. That's always scheduled during the scheduled lecture hours for this course. So you can find it in your personal Tilburg University schedule, your timetable, I should say. Just join there or send me an email. Good luck for this week again for the practice assignment. Starting from week 4, those practice assignments become a bit longer. But I would say just follow the checklist, do things step by step, and use this video for seeing how I do things, what different things actually mean, how you should carry them out, because the checklists tell you what you should do. But now I hope, for at least for multiple regression, you know a bit better what to actually do. I'll probably start making some more of those videos for the other analysis, like the ANOVA, so repeated measures ANOVA, for instance, and the mixed ANOVA, but that will follow later. So for now, enjoy your week, enjoy your day. Make sure to go outside a little bit every day for a walk and not to stay inside all the time in those crazy times. And as I said, always feel free to email me about anything, basically. All right, then that was it. Nice to talk to you again, and we'll probably be in touch soon again, either via email or in the Q&A session. All right, ciao.